So hello again, welcome to lecture 3 on finite element method. In this lecture, we want to continue what we have started in the previous lecture, and that is our discussion on understanding, let's say, understanding the key elements of finite element method via spring combinations. So still we work on springs and combinations of springs. But as I mentioned previously, the goal here is to pick up where we left off in the last lecture, but also to make it more automatic, to make it, let's say, computer oriented, if you want. So we want to go from our, let's say, intelligent understanding of assembling springs to something that is not so intelligent, so that we can code it, we can program it, and that would be sort of a computer-based algorithm. So that's the idea. Now, to remind you a little what we have done, so this is from our previous lecture, a little overview of what we did. So we talked about springs and we said, well, springs can be written as little elements in finite element method. Again, elements of finite element methods are more complex than springs, but springs, they make a very good representative or a very good representation of finite elements. And then we said, well, if you think of a spring, it's basically an element, it has nodes, and then on those nodes, you can talk about displacements and forces. And then if you connect those displacement and forces, you end up with a system which looks like this. And it turns out that this system and this sort of representation, it holds for any element in finite element later. And that is what we will see eventually. But also then we talked about combining these springs. So if you have two of them in parallel, two of them in series, and then a more complex combination, what's going to happen for these ones? Then we talked about that. We said, well, if they are basically two springs in parallel, what you need to do, you write each of the elements, and then you would say, well, now the forces at each point, at each node, is the sum of the forces of the elements acting on those nodes. And then by doing that and doing a few mathematical steps, you can define the effective stiffness as we had known before, and that would be K1 plus K2 in this case. And then also we talked about two springs in series. Now, if you have two springs in series, the procedure is formally identical to what we have done before. Basically, you just write the systems for each of the springs, and now you put them together, you assemble them into a global system, and then on that global system, you impose the condition that you have no force at node 2 or no external force, which makes these two springs indeed two springs in series according to our definition. And if you play with that game a little, you can calculate the effective stiffness, which would be also what you have known before. And then again, in all of these examples, it turns out that the stiffness of the system, whether it is element-wise or whether it is global, the stiffness of the system is always having these nice properties. It's always symmetric, it's always zero determinant. And later we will see that zero determinant is actually a problem for us to solve a system, so we are going to get around it. Okay, so, and then we talked about a more complex system. So we said, now, if you have a system like this, what to do next? And then again, the process is formally identical. So what we did was to write the stiffnesses for each of the elements one by one, and then maybe you can identify these by the colors and so on. And then you add these elements together, or you assemble them, and then also you impose these conditions that, let's say, the forces are zero at certain nodes. And by doing that, instead of a system with, let's say, 5 unknowns, you would have a system with 2 unknowns. And for a simple case that you assume all the springs are having the stiffness of 1, that global stiffness would look like this. And then basically the idea here is to replace it with one spring with the effective stiffness of the system, and then calculate that effective stiffness from what we have done before. And if we did that, then you can calculate the effective stiffness of the system. And some of you actually pointed out here, I have made a mistake in this example. I don't know if you tried it, but this is not 1.5. This would have been 0.5. So it was just a, let's say, a typo. Okay, so these are 0.5 altogether. And if you did it, you would have calculated it as 0.5. Okay, so basically that's the idea. Now, you in this system, you would say that effective stiffness is 0.5. All right, so this is what we did in the previous lecture. As I mentioned, we wanted to extend the idea of, let's say, a element-wise or a spring-wise finite element into combinations of springs. And what we want to do in this lecture is to kind of continue along that line and see how we can make this process more algorithmic. Okay, so we want to do an algorithmic process for that. So let's say the title would be towards an algorithmic approach to assembly. We start today and we finish on Friday, by the way. So we only open the discussion today. We cannot finish it. But as I mentioned previously in the previous lecture, the idea here, or the way I'm going to teach finite element, is to simplify it for you. The idea here is to make finite element method digestible for you. Okay, I don't want to overload you with mathematics. You will learn a lot about the mathematics of the finite element method, but for me, it's more important to explain it in a way that you can follow what's going on, and I will do that with a lot of examples. Now, a very good example to explain the assembly process is if you think of, let's say, two people here. So you're familiar with my drawings, I guess, from E231. And so let's say you have these two people. Now, each of them have a name. Let's say this is person A. I mean, that person has a name, but let's say the name is A here and the name is B here. Now, each of these people, they have a, let's say, a right hand and a left hand. I'm writing right and left for the person. So let's say as if they are looking at us. So it's not our right and left, it's their right and left. And each of these people, they know where their hands are. So now think of, again, in your head, you should always think of an analogy of two springs. So let's say you have now spring 1 and spring 2. And these springs could be these two people. And then right and left hand, these are basically now right and left nodes. Okay, so this would be, let's say, spring A, spring B, and then this would be right node, this would be left node, this would be right node, this would be left. Now, in this picture, you have 4 nodes. Okay, so far what you have is 4 nodes or 4 points. Okay, so you have, let's say here, if you think of this hand, there are 4 hands, and if you think here, there are 4 nodes. Now, what happens in an assembly process is more like this: that these two people, they start holding each other's hands. Okay, So let's say that's what's going to happen. What's going to happen is now these people, they hold each other's hands. Now, for us, looking from outside, we won't be able to distinguish between those two hands anymore. This is, globally speaking, this is the same point. This is one point, and this is one node. But each of those people, still they know if it is their right hand or left hand, right? So this is exactly what's going to happen here in our assembly process. So let's say when you have a system like this, now you would call this node 1, node 2, node 3. Now these nodes 1, 2, and 3, these are global numbering of nodes. And these are, let's say, arbitrary. You can number them any way you want. But when you go to element A knows that node 2 is its left hand, is its own left node. And element B knows that node 2 is its own right node. So basically, what I'm trying to say here, and I want you to look at it that way, is that node 2 is a global node, but it can be written as, let's say, right point or right node of element 1. And now I'm going to put a number 1 here, by the way, and left node of element 2. So again, right and left are something that we can identify when we talk, but let's say every right is 1, every left is 2. So for an element with 2 nodes, I mean, they don't exactly have right and left, obviously, right? I mean, right and left is just our understanding or our interpretation, but they have their own numbering, right? So basically, what happens here is that the global node 2 is node 2 of element A and is node 1 of element B. Okay, so keep that in mind. Now I want to take this one step further. Remember, I just said instead of right and left, let's call them 1 and 2, because these are more, let's say, mathematically correct, and that's the way we can enter this information to computer. Now we are going to do the same thing with the elements. I mean, elements are not A and B anymore, right? So it makes no sense to just have them as numbers, they as letters. They would have also numbers. So let's say this is now element 1 maybe, and element 2. In this course, when I want to talk about the node numbers, I draw a circle around them to identify they are node numbers, and I draw a square around element numbers, okay? So this 1 here is element 1, this 1 here is node 1. And then I remove these right and left to make it more, let's say, mathematically meaningful. And now remember also downstairs we had A and B. Now those A and B would be 1 and 2. So you can think of it as this. Let's say this is N and this is N maybe. So if we write something like this, this means node 2 of element 1. So the superscript is the element counter. The subscript is the node counter of that element. So in summary now, what you have here is this, that for instance, node 2, please pay attention when I put just 1, 2 here. This is a global number. Okay, so let's put it this way. Superscript So everything, let's say upstairs, it's global. Everything downstairs, subscripts, are local. Okay, so when I write n2, first n means node. Now 2 is a superscript, that's a global numbering. So that means the global node 2. Global node 2 is exactly this point. So we know where we are. Now, global node 2 is also node 2 of element 1, which is also node 1 of element 2. Okay, so pay attention now when I have two indices, let's say when I have super and subscript. Now the superscript is the element number. Okay, so if it is only one script, let's say if it is only superscript, this is global node. But in these two cases, this would be global element. But it's in any case, it's global. Okay, so this thing that superscript is global and subscript is local is something we stick to in this course for, so that we know exactly what we are talking about and we don't get lost in, let's say, in our notations. So do you have any question? All right. So now, why are we doing this? Obviously, as I mentioned before previously, this idea of left and right and one and two, it may be useful for just springs, but you can imagine in general, these are not really the best way of talking about elements. But it turns out that what we just did is very, very nicely generalizable to 2 dimensions, to 3 dimensions, to elements with more nodes. Again, in terms of people or these persons that we have here, if you want to think about it, it's more like now, instead of just counting their hands, you want to count their legs too. Okay, so again, each person would know that they have a, let's say, right and left leg, but they won't confuse these two, right? Because one of them is a right hand, one of them is a right leg. And they don't confuse these two lefts, because again, one of them is left hand, one of them is left leg. So each person, again, if it has four, or if he or she has four information, he knows the orientation of those informations and what they are. And that's exactly what's going to happen if we have elements, if we have 2 dimensional elements. So instead of springs, if we have, let's say, an element like this, an element would have 4 corners. But then in that case, what we are going to do is to distinguish between them in terms of orientation. So we would usually use our, let's say, counterclockwise orientation to number them. And then in this course, usually we would say, this is node 1. Well, it doesn't matter which one is node 1. Sometimes you can think this is node 1, this is 2, this is 3, this is 4, or any corner could be node 1, and then you start counting in a counterclockwise fashion. Okay, so these would be the 4 nodes, and then let's say this would be element, I don't know, this could be element 7. And again, remember that 7 would be in a square. So element 7 would have 4 nodes. And that's okay, because once you write it like this, and now if you have another element, let's say below it, and let's say that is element, maybe element 10, And that element 10, it also has its own node. So let's now count it from this corner, 1, 2, 3, 4. Now you can play exactly the same game that we just played previously. You see, now if you put these two elements into or next to one another, if you glue them together, these two nodes will become one, and this would mean node 2 of element 7, and this one would be node 2 of element 10. And then you basically compute the stiffness corresponding to that degree, and then you add them together, which we will do just now, but I want you to have this bigger picture first. And then if you look at these ones, it's the same story. So now, from the upper element, that would be node 1. So it's node 1 of element 7, of global element 7. It's a local node 1 of the global element 7. And then it's local node 3 of a global element 10. Okay, so as you can see, the game that we played is not spring dependent, and that is kind of what I promised, that we use springs to explain what's going on, but everything that we do is usually also generic enough. So we are not sacrificing the generality in this course, and we will do that in next lectures. Or let's say in the second half of the semester, we will talk about two-dimensional elements, and we will see that all these discussions are useful too. But for now, it's mostly 1D. So I write these 2 points. So the first point here is that elements do not have left and right, but that's not a problem, because they would still have an equivalent quantity that is rotation, basically. Okay, so so let's say alternatively, they have not rotation, orientation, sorry. They have orientation, so they know how they are oriented. And as I mentioned, in this course, for simplicity, we usually assume some sort of counterclockwise numbering. Let's say node numbering. And to be clear, this is local node numbering. So when we number the nodes of an element, we have that. Okay, so that's one thing. The second thing, also next to that, is that elements do not have names. I mean, in this example, we talked about, let's say, person A and person B. So obviously, elements do not have those informations, but they have something better, so they have numbers. So again, that's an identifier for us. So elements do not have names, but alternatively, they have numbers to identify them. Now, it's even better that they have numbers. So first of all, because the number of names are limited, but the number of numbers are not limited. So you can have many, many more elements if you number them instead of just calling them. But also pay attention that these numbers are now global numbers, okay? And this would have been our, let's say, our superscripts here as we talked about it. All right, so this is essentially our first story that I wanted to tell you. The first story is that if you want to refer to a global node, you can always find the, how is that? Find the corresponding nodes that are local to that global node. So that is the idea. That's what we want to do. So I clean this up and then I just do a quick example so that you can see what I mean, and then we do a more interesting example together. Okay, so let's say you have a system now, and you have a bunch of elements. They don't have to be strings. They could be just usual elements. So you have these elements connected together. Now this is element 1, element 2, element 3, element 4, and as I mentioned, maybe to be clear, let's put these squares around them. I mean, later when we advance a little, I don't draw the squares because it would be clear. This is the number in the center of elements. And then we have these global node numbers. And for simplicity, let's also number them in the same order from left to right. But as I mentioned, these are always arbitrary. Now, if you think about node 3, you can see that node 3 is, let's say, node 2 of element 2. So again, if you think of element 2 as being just this, so this is element 2. Element 2 has its own local numbering. And then again, for us in the local numbering, for simplicity, let's say all of the nodes, let's say on the left, they are 1, all of the nodes on the right, they are 2. So node 3 is basically node 2 of element 2. Node 2 of element 2. But also if you draw a similar picture for element 3, again, that element 3 has also its own node 1 and 2. And then you can also say, well, now from that perspective, node 3 is also node 1 of element 3. And you can imagine this game that we played, it's very easy, because if instead of just 2 elements on their right and left, I mean, if you had a bunch of other elements attached to that node, this thing would always work, right? You can always just generalize it. It's a numbering. It doesn't have to be 2. It could be 10. Okay. Now, this is a crucial step for us, because basically just doing that, it allows us to say that, just for simplicity, let's say, the stiffness of node 3, again, this is a very sloppy way of saying it. It's not very precise. We will have more examples and we understand what I'm saying. But just in a, let's say, in a simplified manner, you can then say, well, then stiffness of global node 3, so stiffness of global node 3 is then the stiffness of element 2 at point 2 plus the stiffness of node 1 from element 3. Does that make sense? So basically what's happening here is that you have a node that is shared between 2 elements. So if 2 elements share the same node, they both contribute to the stiffness of that node, to the resistance of that node against displacement, right? Stiffness is resistance against displacement. That makes perfect sense, right? So that's exactly how this thing is going to work. And now, if just for a quick moment, if you think of having two springs in series, you can see that this analogy is not exactly what we did there, because there we needed like k1, k2 divided by k1 plus k2. So this is more like having these in, yes, sorry, my drawing is, but my drawing was fine, but I said was bad. So this is basically exactly a system like this, just for simplicity. And then if it was two springs in series, this would be like that. So obviously this is not good, because if we did this, we know that if this was the case, let's say if it is K1, this is K2, the effective K was K1, K2 divided by K1 plus K2. But if we have a case like this, so if that point or that node is in the middle, it's more like having two springs in parallel. So in this case, this is exactly what we learned previously. We know that this K1 plus K2. Okay, so this is kind of the story. You can think of this picture as being just this. So the node in the middle, node 3 here, is exactly the node that is shared between these two elements. So the stiffness associated with that node would be then the sum of the stiffnesses from the two springs attached to it. And as I mentioned, if you had 100 other elements or springs to it, it would be following the same thing. So they would just add to the stiffness of that point. And then again, as I mentioned, stiffness of a point is a very sloppy simplification. Obviously, a point doesn't have a stiffness. It's always elements. But to explain what we want to do, I think that's a very good way of looking at it. And also, that's the way we are going to program it later. All right. So that's that. Now, we want to kind of look into an example and play with this a little more and see how the information that we just learned is going to help us to assemble a system together. So we want to do an example. Or let's say a more complex example. Everything was example until now anyway. So well, that's it. Now let's think of a picture like this. In order to have it more, let's say, understandable, I'm going to draw it as if it's a 2D picture. Obviously, it's a 1D picture. But I'm going to kind of draw a wall. I mean, a wall basically means that the points that are attached to it, they have zero displacement and they are connected together. So let's say you have this as point 1, and then okay, sorry, let me start here. So this would be the first spring, maybe K1, and then it's attached to other springs. And as I mentioned previously, we are going to learn the key elements of finite element method using springs, but you can always try to solve such systems using your previous knowledge of combining springs. And you can maybe then appreciate actually that finite element is pretty useful because it allows you to also solve more interesting spring examples quite easily. All right, so that's that. And then let's say these points are also attached together. And then here well, these points are attached together. So again, this is the same point. So if you want, you can think of it as if you have two springs and then you connect them to the same point. Okay. And then on that point, you apply displacement. The same thing holds for the left end. So you may think of these two ends as just being two springs attached to the same point. Okay. So I give one number to that point. All right. So on that point, we are going to apply a displacement on that wall. And what we want to do is to compute the effective stiffness of this system. And as I mentioned, this is basically the picture we want to look into, but it's important that you understand that these points are connected together. So I'm going to maybe redraw it according to that to just have it more clear, but you get the idea. So if later in your exercise or in your exams you see walls or straight lines and so on, you shouldn't be surprised. It's the same thing. It basically means these springs ending there, they have the same displacement, so they are ending at the same node. Okay. And maybe just to be clear, we can do the same thing here. So it's like that. All right. So this is then, let's call this element 1 or stiffness 1. This is element 2, stiffness 2. Maybe a stiffness 5, stiffness 4, stiffness 3. So these are elements. So this is like element 1. So it has the K1. So K1 is the stiffness of the element 1. I don't want them to be equal necessarily or give them numbers. So that's why I call them K1, K2, K3, K4, and K5. But you should distinguish between element numbers and stiffnesses. So the squares are element numbers. And now you would also need to add node numbers to the system. So let's say this is node 1. And then in this example, later we assume node 1 is fixed. And at the end, we have node 4. And also in this example, later we assume that node 4 is under a displacement U. Okay, so basically, we want to think of a spring which looks like this. This would be eventually node 1. This would be node 4. And as I mentioned, this would be fixed. You apply a displacement to this, and there would be an effective stiffness for the entire system. And that effective stiffness would be the stiffness that we calculate for this system. And the other nodes, well, this would be node 2, and this would be node 3. So you have 4 nodes, but 5 elements. Now, what we want to do is to compute the effective stiffness of this system and then calculate, let's say, for a given displacement, we want to calculate forces and so on. So how can we do it? We do exactly as we did previously in our previous lecture, but we use the numbering that we learned today to connect these things together. So let's say if you think of element 1, so first of all, see, I am writing this as a bold letter. So bold letter stiffness is the stiffness matrix. So element 1 has a stiffness matrix composed of 4 components. And those 4 components would be K1 minus K1 minus K1 and K1. All right, so this is element 1. just push it a little to the side. Okay, so I hope I have enough space to write all of them. So I'm going to now duplicate this for other elements and write them. Now, if this thing was element 2, all you had to do is to just replace these ones by 2. So this is kind of element-wise. So this would be for element 2. And then we keep playing the same game. I also changed the color to distinguish between them maybe. Now, you write the same thing for element 3, element 4, and eventually for element 5. So this is element 3. Okay, let me go to the next page. I'm going to remove this little picture here to write 5 there. But also I still need to change the colors because, I mean, later we will use these colors when we want to distinguish between them in the assembly process. All right, so this was element 4. So these are all K4. And then you have the green one, element 5. These are all K5s. All right, so this is what you have now. So what we want to do is to assemble these into a global matrix, global stiffness matrix. And that global stiffness matrix, we know it's going to have, well, 16 components. So it's going to be a 4 by 4 matrix. The question is, so let's say the effective stiffness, the global stiffness, is going to be 4 by 4. So I'm trying to draw it large. So this is going to be 4 by 4. And then on that one, we would have node 1, we would have node 2, node 3, and node 4. And then also here, maybe node 1, node 2, node 3, and node 4. But then, as we spoke previously, each of these nodes, so let's say if you think of a connection, or if you think of a node 2, so here you would have a stiffness 2, 2. You can't expect that at node 2 is here. You can expect that at node 2, you would have contributions from element 2, from element 4, from element 1. And using what we did today, I mean, we are going to number this shortly. this is going to be a very simple process for us. So what we want to do next is to identify these, let's say, we want to identify the global number associated with every local number of the points or of the nodes. That's what we want to do. So let's say what we want to do next, and that's not something that we are going to finish today, but I just want to kind of emphasize what is the next step, and you can actually try it on your own, and then in the next lecture we can quickly do it together. But it's like this. For instance, think of this one. Think of element 3. If you think of element 3, it's here. It's between global node 3 and global node 1. Okay, so what is going to happen later is that the components of that element 3, the components of that, remember we said it's between 1 and 3. So if you think of this, that stiffness, that element has 4 components, right? It has a component here, here, and here, and here, right? Those 4 components, which are K3 minus K3 minus K3, K3, those 4 components, they actually come and sit here, because they know their global associated numbers. Okay? So that's the idea. What we need to do is very simple. You basically clean up these element numbers here, and on top of each of these, you write a global number, or you write the global number associated with each of these elements, and then those are the numbers or the indices that you would feed into your assembly process, and then you calculate your global stiffness. Okay? And you can imagine this is a, we are not yet completely in the, let's say, in the automatized way, but this takes a lot less intelligence. It's basically just numbering. And if you did the numbering right, so all you have to do is to find those associated numbers. And once you have the associated numbers, you just throw them one by one to the next element. Okay. So long story short, I think it's very important to see it this way. In the previous lecture, we started from what is inside, and then we went out and we fished out what we needed from the elements. Now it's the opposite. We actually go element by element and distribute the components into the global stiffness. Okay, so if you want to think of it as a programmer, or the way you program it, what we did in the previous lecture was more like a loop over nodes. What we do today is more like a loop over elements. So we go to element 1, we distribute its stiffness in the global stiffness. Then we go to element 2, then we distribute its stiffness into global stiffness. Then we go to element 3, element 4, and element 5. Okay? So it's just like a loop over elements, and then later that's the way we are going to write it in our programming. And by having those, let's say, the corresponding numbers, it's very simple. So you don't need any intelligence. And again, having no intelligence or being able to do it without intelligence means that you can program it and your computer can do it, or your calculator can do it. And that's exactly the goal here. All right, so I'm done for today. As I mentioned at the beginning of the lecture, this was something I wanted to start, but I knew I wouldn't be able to finish in one lecture. We will finish this and we will kind of wrap up everything in the next lecture on Friday. Do you have any question? Very good. Thank you very much for your attention.